Let's just have the panel introduce themselves. Wen Mei has already done that. You know who he is, but Perry, let's start down at your end. Who are you and who do you do it?
Well, I introduced myself yesterday. I think everybody was in the room, but so I'm Per Nyberg and I work for Cray.
Hi, I'm Joe Curley with Intel. I have done a number of things, but most of my career has been involved in building what has become Intel Xeon Phi, or on what people are now referring to as code modernization.
Wen Mei Hu again. Bill Kramer with the Blue Waters Project.
And Tim Carroll with Psycho Computing.
So Wen Mei, you sort of teed up this GPU CUDA. There's a way to do some things here. So Joe, I want to start with you. You've got this alternate, you know, it's not a GPU, but it's a different architecture. Could you just describe Intel's elephant in the room? What's been the thing that you've tried architecturally to solve? What does that look like, et cetera?
Okay, so let me take a crack at it. I think one of the first things is that I mentioned I'm working on Xeon Phi, which is a many-core processor. So I'll talk about what many-core is briefly. But just for one thing that's maybe a little bit misunderstood is Intel makes GPUs. In fact, Intel makes CPUs, GPUs, we have CPUs with FPGAs integrated in them. We do a lot of different solutions. Because sometimes it's actually worthwhile to go through the trouble and the pain of the hardware-specific coding that Wen Mei was talking about, if the benefit is good enough to write. The QCD guys are a great example. They'll write to register files and rewrite their code all the time. But I think I think Wen Mei and I might argue over some parts of some givens in the argument. We actually agree wholeheartedly on one thing, which is that for the vast majority of applications, you really don't want to port either to a piece of specific hardware. You do want to gain power performance breakthroughs, and you don't want to deal with some of the system level complexities of offload and other things. So what we're building is a highly parallel instance of an Intel microprocessor. It runs operating systems, hosts users. You know, it's a CPU. But it delivers the performance levels that one expects to get out of a highly parallel accelerator, but it uses common programming models. Now, one of the other things, so Xeon Phi is, just think of it as take a Xeon, but make it a very throughput-oriented one with a lot of vectors and a lot of throughput, and as long as you can fill it up, you get a lot of performance. By the way, if you don't fill it up, you don't. The second thing that we spend an enormous amount of time on is trying to work on programming models and scalability, because for us, nirvana is that we can yield a code that in any basic general purpose or CPU architecture, by that it's based on cores, caches, threads, and SIMD or some form of it, that you can't actually port that code across. So one interesting example of that was we got a call from part of SIDAC in the government last week, and the guy was laughing at us and said, "Oh, you're going to really hate me. We took your Xeon Phi libraries that we built for QCD, and we just ported them all to Blue Gene, and Blue Gene's running great." And we said, "I love it." Because the reason is that we actually structured code in a way that anything like a Blue Gene, which is a very different machine than what we're building on Xeon Phi, that the port was very direct, because the way the code was structured in general languages through loops and through saying what's vectorized and what's threaded actually moves very well between those kinds of machines. Now when you jump to a GPU, very, very different world, but as long as you stay in the world of CPUs, you have a lot of portability. So we're building what we jokingly say is we'll see if you think of it as a poker bet, I'll see you on your power performance, but I'll raise you the benefits of common programming models.
Mm-hmm. Bill, you've done some heavy research into what follow-on machines to Blue Waters looks like. You shared a bit yesterday about what that challenge was just in architecting Blue Waters in the first place. So how do you see this landscape? What is promising, what's not, in your mind?
So we certainly know that methods of getting more parallelism from the processor, from the nodes, is going to play a very important role moving forward into whatever systems come in. So the challenge is, what are the best ways, what is the best approach, most productive approach for to have a system where it's productive for the science teams to do so, and there's real performance rather than some limited amount of performance coming out of some theoretical performance. So and that could become still be a mix of different types of nodes like we have on Blue Waters today. Some people call those personalities, or it could be going back to a single type of node that does multiple things there. So we know that there's more parallelism, be it a PHY or be it a GPU or be it an AMD implementation in various time frames there. They're all going to present very challenging things for re-engineering codes to get the performance out of the nodes. And while we all love the QCD folks, I would say that that's not a good representation of the challenges of science or engineering teams. They basically have a relatively straightforward, simple problem. They are highly expert. They are highly efficient, but it is not the complexity that exists in weather codes, climate codes, molecular dynamics codes, engineering codes. So what works there is somewhat a misrepresentation of the potential for whatever anybody else can do. So I would like to hear more about how, say, the climate community and weather community might be able to leverage vectors, GPUs or many-core, like you're talking about. With that, the other thing that complicates this is the push on more hierarchies in memory. So that is in part motivated by we have to get more data, more operations into the CPUs for them to act on the threading. But the other part is, I think that there's going to be much more integration with the data and storage activities that we have going on. So the architectural changes may be pushed as much by the external interfaces with data as they are by I need to feed my cores. So that tension, I think, is going to exist in the future systems that we have, not just for something that would be in a couple years from now, but for maybe the next decade until it gets worked out properly. So there's technology, but it's also how the codes will be structured, how explicit that is for the programmers. So one nice thing about the GPUs is you can be much more explicit, and you're not fighting all the virtualization that systems put in to make it easy for some communities, but actually in the high performance area makes it in some ways much harder to do the work because there's less control, so you try to trick things. So de-virtualizing some things in some cases may be easier. So as we go craft these many more hierarchies in the architectures, how do we control that, and how much we try to hide automatically versus how much we allow some control by the programmers, I think are going to be trade-offs. It's certainly the case that if we're, as we move to much more parallelism, the ways of doing that have to get much simpler. So we would very much like to see the synergy between different variants of directives like OpenACC and OpenMP into a single common way that the programming teams can actually write once without having to change things. And that's as much a business decision as it is a technology decision. So we hope that will gel, because that's going to help enable more of our teams to be able to make use of the highly parallel or the GPU environments, and certainly then tool chains are important.
So Cray certainly has done custom building of a number of things. You've done your own chips, you've done your own interconnect and other things. But the path at Cray has changed a little bit, and you've bought some companies and expanded some opportunities. So what does this environment, what's going to continue to change the choices in how we serve the community from a place like Cray?
Yeah, so I mean, certainly you're correct. I mean, a lot of the Cray history was, at one point in time, everything was custom designed, right? For certain three-letter agencies, and it kind of grew out from there. Over time, it's I guess it's this concept of what's good enough, and I think that that's an important one, especially as we think of the sort of this bifurcation in the workflows between the ones who will do absolutely anything for performance and maybe an industry where they're just trying to find what's good enough in order to get their design cycle overnight, right? And I think that that drives a lot of the investments that those different communities are willing to make. Those investments also drive what a company is willing to, design and manufacture. Right, so for Cray, we have to find that sweet spot where you are certainly designing systems for those ultra performance end, but you're also designing systems that are cost effective and deliver the value that's needed by industry, which is better than just good enough for us, right? But certainly they're not going to pay anything and everything just to get the best performance they could ever achieve. So by doing that, from our perspective, we need to kind of pick and choose where we add value, right? And it has been in areas like, interconnect, for example. Obviously today we use commodity microprocessors, but an area that we don't talk a lot about and we should, and I agree with the previous speaker about the importance of software. We still invest a lot of money in software, compilers, operating systems, and that's kind of hidden in the back. People tend to think about hardware, and so I think that moving forward, I agree absolutely with that, and that more investment is required at the software level. That is the elephant in the room, because you look at all the hardware technologies and as others have said, I mean, they're getting sort of, wider in terms of parallelism, but also deeper, right? Deeper memory hierarchies, deeper storage hierarchies, and, it's to manage all those technologies is a software question. And there are going to be technologies that are purely software. I mean, there's almost no hardware. Well, there's obviously hardware there, but, let's say 80% of it is really software. So that's kind of driving the directions we're looking at in terms of where to put our intellectual property in, and again, sort of managing both those ends of the spectrum, right? The ultra performance and the let's say the good enough.
So do you foresee the day you're going to have a software-defined Tesla car, and the supercomputer is going to act like that?
Well, I think it's moving in that direction to some degree. I mean, we've already talked about the concept of kind of services on the edge of a network. And I think, when you talk about this drive towards heterogeneity, even as, standards for traditional supercomputers, you are going to see services becoming, and I think sort of Bill used the word personalities, right? I think you'll start to see that are a little bit more workflow specific. And so, yeah, maybe there is an extension there. Certainly the Tesla car will be one of the data drivers, if you will. But it's certainly becoming much more software enabled. There's no question.
So Tim, you represent not a hardware vendor. You really do represent a new on-ramp for a lot of computing. So some folks think the cloud's just the boogeyman here, and we really can't do, we heard Luda say something earlier, this is not going to happen in the cloud, but what are you seeing from your chair?
Let me step back and give a little bit of context. So 4 years ago, I presented to the partner meeting in a closed-door session, and we talked about the elephant in the room, and at the time I was running Dell's HPC business, which is a $500 million business. And I used language far more colorful than I will use here, but I told people that the business stinks for the vendor community, right? And that if the business didn't get better for the vendor community, there wasn't going to be no vendor community going forward. And it was just a reality that people who depended upon these platforms for their livelihood were going to need to contend with. At the time, I violated one of my own tenets about bringing up what I saw as a problem and not having a solution, but that was 4 years ago, before cloud was really potentially an element of this, right? Element is not the answer, but it's certainly part of the answer that's complementary to what we're talking about today. Last year, our software orchestrated 400 million compute hours on a variety of publicly accessible compute platforms. We'll call it that, right? So the reality of it is that this is happening one way or the other, right? And what I think is what's going to be a lot of fun to watch over the next 5 years is that if you take a look at what happened in the transition from supercomputers to Linux clusters, and just by way of context, I was at Linux Networks, and we put the first production system into the Department of Defense in 2003. And I spent most of 2004 and 2005 at the HPC, at the mod office meetings, having to sit at the kiddie table at Thanksgiving because nobody thought we were real technology. It was a stunt, right? And the reality of it was that, 10 years later, we had a $500 million business somewhere else. And the reality of it was that it was the users that embraced us, not necessarily the people that were setting direction. The 400 million hours that we sat in front of are all user-driven, because everything that we do comes out of financial services, life sciences, pharma, and manufacturing. And so what I think is going to happen here going forward is that we're going to see a shift that's even more dramatic than the shift was from supercomputers to Linux clusters, and it's going to take half the time. And it's going to be entirely user-led, because the people that use public cloud to solve problems, they got two things. They got a problem, and they have a deadline. And that's all they care about. And so the great part is that what everybody talks about in terms of software, that's what's going to help people leverage the literally millions of servers that are being deployed by cloud service providers. And if you listen to yesterday's study about that people's needs are going to go up 10,000x in terms of their computational requirements, there is no way that anybody here is going to deploy enough hardware to meet the needs that are coming down the pipe, especially if you are constrained not just by budget, but by the size of your data center. So there's going to be no choice for both industry and science to figure out how to leverage the millions of servers that will be accessible in a way that you can turn them on when you need them and turn them off when you don't, in order to get science and to get work done.
Compelling story. Wenmei, if you would just sort of add to what was teed up here a little bit, then we're going to throw this out to questions for the audience.
Yeah, just a couple of things. Talk about software. So one thing that at least the academics see today about cloud is that when we look at the cost of these hardware systems, the interconnect cost is actually coming down real fast. So in many ways, when we look at cloud today and we say, okay, one of the reasons why we don't like cloud is because the interconnect doesn't give us the kind of the latency and throughput that we want for this cluster computing kind of situation. But my prediction is in the next couple of years, we'll pass the point where the cloud can probably offer very similar latency and throughput compared to some of the proprietary clusters.
Yeah. I think that for the purposes of from a user perspective, even if it doesn't, that's okay. Because there are a bunch of things that are running on clusters today, on internal infrastructure, that shouldn't be, right? What we should be thinking about is, rather than trying to figure out if we can bring these other things up to parity with what's sitting here, let's take the workload. Here's the opportunity that we have over the next bunch of years, is the people who are responsible for getting these workloads run have the opportunity to decide whether it's going to run on a supercomputer, whether it's going to run on an x86 cluster, or whether it's going to run on the public cloud. And I think that virtually everybody's going to have that entire portfolio available to them. And we're going to, for the first time, we're going to reach that aspirational goal of being able to match the workload to the right platform for it. And that's where real price performance comes from. Price performance doesn't come from how badly can you beat down your cluster vendor to try and build a system that will serve the greatest number of people. Match the workload to the right platform, and everybody wins.
That's his story, and he's sticking to it. What do you think out in the audience? Microphones are available. Ron's up first.
Yes, okay. I'd like to sort of take that discussion and perhaps extend it a little further.
Microphone's coming your way here.
So I'm a diehard fan of HPC and big data centers. Enjoyed the tour last night. Understand the principles of low latency. I like the arguments around cloud, and perhaps there's a lot of applications, probably a faster growing set of applications that don't need that low latency and can run in the cloud. So my question is, let's take that one step further. Most of our phones have 4 or 8 cores in them. The network latencies in the wireless network are going down as well. Social sciences is rapidly adopting parallel programming paradigms to do social sciences research. So can we use HPC techniques, parallel programming techniques, to perhaps build applications or apps that would leverage hundreds of thousands, millions, hundreds of millions, perhaps a billion devices to do social science research? What's the future there? Maybe we call it cycle harvesting, maybe we call it something else. But I'm wondering what the logical extension from cloud is to the Internet of Things, these smart devices that are numbering in the billions. And do we see data applications that span a billion devices that could do things that nothing else could do?
Great question.
Yes. So, no, just anecdotally, so I've got a bunch of friends who work at Under Armour, and they just bought MyFitnessPal. So MyFitnessPal is an online tool, you work out, et cetera, et cetera, et cetera. They have a group, a software group. They also have a hardware group who's building Internet of Things type data collection devices to put into the apparel that they're selling. The reason for that is to be able to collect data that then turns into actionable device. So the reality of it is that the way that I hope that everybody's looking at these workloads is that, whether it's 5 or 10 or 15 years from now, people aren't calling it HPC. It's just big compute. It's just solving big problems that need more processors than we currently have the ability to throw at it. And I think that once you uncap people's thinking so that they're not bound by what they think they have in their data center, things get awesome in a hurry.
I mean, I think some of this has to do with, what's done with the data, right? The data in itself is interesting, but it doesn't really necessarily create any value of its own, right? And I think that, so yes, you're collecting from all these millions of devices, but sooner or later, what's most interesting is the relationships between these devices, right? Or the data being gathered by these devices. And that's actually a very difficult compute problem, right? And I think that's, so I think what you're seeing right now is a proliferation of, data, collection points, whatever they may be, phones or mobile devices, but it's what people do with that data and what value they create. And then this is an industrial problem as well, right? And I think companies will start to outcompete each other as to the intelligence that they can gather out of that. Because again, the data in itself is...
Yeah, we have a number of projects that use graph theory,
Absolutely.
And some of them are adapting that across the networks as well. So,
so
I think there's tremendous potential there.
Absolutely. Sorry, just one thing. So Merle asked about create custom hardware. Well, a few years ago we designed a machine specifically for graph analysis, and it's this is a very complex problem, very, very complex, and in some ways, when you scale this up into the billions, its computational complexity outstrips just about anything that's done in other science domains, right? And so that'll create new classes of computing or computing solutions that'll solve those types of problems.
Yeah, so one of the things I think we might be able to do is have HPC, you might be able to learn from some parts of work that's going on in canonical HPC for this social, big data, deep learning, which buzzword do we want to use, problem that you describe. If you take a look at some of the projects that people are looking at, whether it's the Square Kilometer Array or what CERN is doing, they've taken a very interesting view of what computing is done at the edge, what are you doing with the data at the edge. If you've got a little bit more brains at the edge, what do you do there? How smart can you be to minimize what you're sending up upstream to get further analysis and further types of activity being done? So it's very likely that there's not one particular answer to this problem, but many, and there's probably going to be one of those distributed problems. I think the good news for all of us is that it's that gold mine of, we don't want to call it a data tsunami, so we don't get risk the wrath of panelists. But we have all of this kinds of data that we can discover from, and we are building out. The reason we're talking about all of this brand new hardware and the problem of modernizing applications and why are we talking about exascale or any of this stuff in the first place? Where's the relevance? Is that the amount of data that, to have exaflops, you want exabytes, the amount of data that we're going to have, the types of parallel machines that we're going to have are actually going to be able, in the data center, to be able to, or in the HPC system or in the cloud, are going to be able to grok on it. So the reason we're doing all the hard work is to build out the infrastructure that you can end up having that kind of distributed solution with. But what people will do with it, I don't know. It's kind of, let's put a bunch of canvases and easels and paint out and see what people create.
Yeah, I think that's really good. But our organization funds a lot of campus-based accelerators and startups. And a lot of these are brilliant programmers, and they're thinking parallel, but they don't even know what MPI is.
Yeah.
And they are programming for edge devices and in the cloud. If it's all right, one more question on a kind of a completely different slant. I mentioned this to Merle.
Can I comment on your previous question before we go on to the next one?
Sure.
So it is true that many things are now being distributed in a different way, not in a tightly coupled synchronous way that we use MPI for. And many of the methods that had been in the past HPC methods now are able to run in other places. But I just want to give an example of something. We have one of the projects on Blue Waters with millions of node hours, 100 million or so core hours a year. And it's a researcher from Stanford, Vijay Panda. He is one of the originators of folding at home. And his project on Blue Waters is folding proteins. So why is he doing both? Maybe he didn't get enough homes to sign up for folding at home. But it turns out that's not the case at all. So in order to enable folding at home to work, there has to be a lot of much more intensive computational, highly parallel, synchronized preparation for all those structures. That's what he's doing on Blue Waters, and it's a big data part of that. So he can send out little pieces of data, and you compute on your PC or your edge device. But that's only enabled because the heavy lifting is done on still highly integrated machines. Yeah. So while I think there's an awful lot of potential for doing these things, certainly in the data collection and analysis, in the end, that only, or much of that becomes feasible only because there's also heavy lifting going on there. Another example is cloud providers have lots of things that appear to be instantaneous, right? But that's because behind that, there was a lot of planned high performance, maybe not MPI, but high performance computing done to prepare the data so the query looks like it's instantaneous. And e-insurance is the example, right? They pre-compute everything that you go query, and that's a multi-day computational problem in the background that they do every week. But what it appears is, the cloud just gives me the answer immediately. Mm-hmm. So there's a lot of things that have to be enabled by the larger scale, more concentrated resource to enable what you want to do on the edge devices.
Okay, thank you very much.
And when May, you look like you're itching to say something on this topic as well.
I was going to just make a quick comment. Vijay Pandya and I were chatting about folding at home a few years ago, and our conclusion was that whenever you have something that you can send to a device and let that device kind of crank for a while, it's a viable model. And so you can think about it as an extremely slow PCIe bus connecting to something else. And you know what? For now, when we look at offloading, this is a super offloading model. And a lot of times these data models, as Bill is saying, they really need to be totally finessed and so on, so that you can do the graph partitioning enough to enable this kind of model. But it definitely has its place, and if you can get enough people to sign up, it can be used for some of the problems, especially when there's no funding for some of these other, some of the computation. This can be a slow way of getting something done, right?
So the other completely different question was what the panel thinks looking forward of neuromorphic computing. There's been a lot of buzz about that lately with IBM and with Stanford and other chip manufacturers. So just how far out is that, and what are the issues with that?
Must be pretty far.
Right, exactly. I'd like to recuse myself from that answer right there. I'm worried about next year.
You yield your time.
Right, I yield my time to the senator from Portland.
So I don't really know, but we just mentioned we're still now have the first time some examples of quantum computing that are implemented, and that was theoretically, and there was some very simple examples a long time ago. And I saw something, you need 512 qubits and you can solve any problem in the entire world, came out as a theoretical result. So I would guess it's not going to be in the time frame of the Blue Waters 4 or 5 machines, let alone Blue Waters 2. So
I'm probably going to regret for saying this, but I'll say it anyway. Neural networks and neuromorphic computing are excellent when we don't know how to do something with a computer. Whenever we don't know how to do it, here is a black box, and we can feed some data through it, and then the past will predict the future, and then we have something. And the problem is that oftentimes it's hard to reproduce results out of these things. So if something goes wrong, we don't know how it went wrong. But I'm not saying that in a lot of our human systems we can reproduce things either, right? So that's not what I'm saying. But I was talking to someone in the automatic driving vehicle world, and one of them said, we can imagine that some of these neural net kind of things can get us better percentage of, let's say engineering of, vehicles and so on. The problem is they don't have enough ability to engineeringly quality assure and then reproduce problems. So if something goes wrong, they don't have any way to assign responsibility. And in the human case, we have laws and we have all these things that deal with this kind of problem. But when it comes into engineering, there's whole infrastructure that is missing in terms of this kind of paradigm. So I don't see that as a strictly an engineering problem. It's really, if you look at the liability and the requirements and so on of our engineering systems, I don't think we're quite ready to deploy those things, except for the kind of the fun things where people look for cats. I think that will be primarily the most visible application for a while because of this lack of infrastructure.
To the direct question, I don't know, and if I did, I know I couldn't say. But to the indirect question, there's a lot of other. We're actually in a time of great innovation right now. And I'm glad Bill brought up the quantum computer. And there's a, if you have a programmer with if you have Smilyansky able to to program it, you can actually get a working application. But over time, we can work on that. But we're in a time of great innovation in the industry right now. Not only, clearly the company I work for, Intel, is doing a lot, but we're seeing new processor architectures, new programming models, new machine architectures, new ways of trying to address problems. I don't know that it's ever been as fertile a time. In the short term, though, we've got some really practical problems we have to deal with. They may be considered yesterday's problem because we all wrote it down on a paper in the end of the 2000s. We said, we've got a memory wall, we've got a programming problem, we've got power efficiency, we've got architecture issues, and our networks don't scale for the machines that we're going to build. So before we worry about the next big problem we're going to go solve, we're really still very much in the world of solving those problems. We'll only start seeing the answers for them now over the next 18 months. So look in the short term, look for great evolutionary change from many parties, and then that may bring us a path to some more creative solutions down the road.
So what I'm a little worried about is that we're pushing on the wrong end of the wagon. It feels to me like a lot of people are, because it's hot and cool and all that, and we're pushing on the tongue. So as a manufacturer who has to move wagons, right, here's the economic reality. It costs $100 to do an experiment and have a bunch of engineers. It costs $10 to pay for the engineers themselves to do analysis if you want to replace the virtual. It costs $1 to buy the software, and it costs a nickel to buy the computing. It just isn't relevant. Cloud, not cloud. In fact, the only issue, Tim, I'd be really curious is I can't get a price for cloud that's within a zero of what I cost to own it, provided if I own it, I use it. If I own it and don't use it, then it's pretty expensive. But if I own it and use it, fill it up, which is a queuing problem in a big company, essentially, you have to harvest your own HPC, if you will. It's not within a zero yet. And I don't know whether that's because they're trying to build out, make money, buy a boat, or whether they just have a lot of idle hardware. I don't know why, but I'm not within a zero. But the real problem is not the 5 cents. The real problem is the dollar, which is the software. And if we take software and price it as software per core hour, right? And let's do that. I don't care what the pricing model is, whether it's by core or by job or by study or by year or make it up. I write a check to a software company. I have X hours, X people, X computing. If you do software as a cost, and that includes the middleware stack. If I did a cost of dollars per core hour for my software, it's 2 zeros more than the hardware we're farting around with here. And so it's like, let's work on the software, please. So there's 2 questions in there. One is the software, and the second question is why is the cloud still too expensive, or still an order of magnitude too expensive?
So
Go ahead.
maybe just one quick point. Right now, the software per core hour cost is expected to be 0. So that's why nobody wants to work on it. To be very blunt and honest, right? All the infrastructure people, essentially the expected dollar amount is 0 today.
Why? I'm confused by that.
So if
That's what they think it is, or that's what it is? Because in my world, I spend 95% of the compute dollar on software.
That's ISV software, right?
Yes.
Yeah.
Or the alternative is I'm oil and gas, and I have my own 50-person staff that administers the software.
Correct.
So friggin' it doesn't matter, right? It's still the dominant cost.
It's just
That's
measured
correct.
differently.
So if you hire your people to develop the software, maintain the software, and so on, that cost shows up. But whenever someone comes out and look for a software, the expectation is you start from 0. Well,
Okay, but not in a not in anybody that makes anything. That's not true.
that's great news. In fact, I'd love to have everyone to say exactly that, because that's what it takes for the software industry to really do the innovation in the next phase. I totally love what you're saying, to be honest, very much so. Thank you.
Okay.
Yeah, sorry.
Did you get your answer, Tom? You got thanked. So a comment on certainly, there's no point in having software unless you have the physical resources that you would run the software on, right? So there's a sequencing here. So you have to have the physical resources. It's great. It's 5 cents. That's an awful lot of technology that went into making it 5 cents for what you're doing. On the software side, there at least the science and engineering work that we talked about yesterday on Blue Waters, all that software is funded at probably higher levels than your 95 cents. So the groups that are doing the research are also the groups that are developing that software. So that software is being paid for somehow. They're being paid for by the funding to the research groups. And some are explicitly funded to do it, and some are just funded to do research that they have to enable or create their own software. So it's not just an issue of what industry pays for licenses, because you're trying to get somebody else to craft the software and then you do the problems. Open source is perceived as Richard Stallman makes a difference between, he has a free software foundation, and he makes a difference between software that's free and software that's no cost. And I think that that's an important distinction that gets blurred in this whole discussion as well. And he doesn't advocate software that has no cost. He wants software that's open, verifiable, source code, things like that, which is a different thing than you would assume from without hearing what he's doing. But software certainly has to be the enabler to actually do the problems. the first enabler is having enough resource that it's worthwhile running your software on. And the fact that that's low cost and whatever. On the cloud side, I think that, yeah, it's a business model that is trying to, I put it in the same category as the miles of why ISV software is higher than other types of research software, right? There's a profit need for a lot of that as well.
You know, just to the business point that I wanted to make was, remember, the experiment and the test is $100. The clinical is $100. The prototype is $100, right? Computing and modeling and simulation is the, you know, 1-0. So there's plenty of money to buy hardware and software.
Right.
If we can be clear with the science and technical community that you must, that modeling and simulation is not a nice to have and, it is a replacement for the wind tunnel, the crash, right, it is a full out replacement, and you get another 0 when you do it.
I'm glad you said that, because this is where we were going to go with the answer. And in the first day of the conference, we talked about a case where you're reducing the 100 and the 10 with the $1 and the 5-cent investments.
Right.
You know, we showed an example at International Supercomputing about, I guess, middle of 2013, where Audi had utterly changed their workflow, their design process, to eliminate physical prototypes to the tune of 6 months and $1 million per body type, and then another 7 months and something like, and over $1 million per physical fit and finish prototype. They ended up taking years out of the development cycle of a model year, and they removed, you know, millions of dollars of direct cost and tens of millions of dollars of indirect cost of the iteration that you end up doing on the models. If you look at the value to the corporation of hitting a model year on time versus slipping a model year on time in Intel, you think of us as a tech company, but we're a manufacturer. You know, we know what slipping a date inside one of our factories ends up costing the shareholder. And that, so let's not focus on the nickel or the dollar, but how do we use the technology to do both of those things. And the other implication of the reason why we're doing all this, you know, deep petascale and exascale stuff is not just for the 3-letter agencies. The derivatives of that go into your departmental supercomputing with modern applications end up driving your cost and reinventing your process for you at a fraction of the cost of the compute. Whether you're doing it in the cloud or whether you're doing it locally, it's still going to end up being a fraction. So, the big deal, the reason to get on the modern hardware and get the modern software on top of it is to change those $100 and $10 investments.
I mean, if I could maybe just throw something different out on this software topic. I mean, I think your example is perfect. But like I said, I think it's that the software cost is heavily skewed towards the ISV software. So even if you do it within, a national lab where, you're not paying for ISV software, but you're paying engineers, I think those you can kind of compare and measure. But I think what's kind of missing is the cost and the investment that's required to go into the middleware and the operating systems and the compilers and all this sort of enabling software. Doesn't fall anywhere, right? And that's one of my worries is as we become more dependent on all of that, who's investing in that and what's the business model there? It's a little unclear because especially at the national lab level, you have there's a sort of a combination of software that is paid for. It might be a scheduler. A lot of it just comes from the vendor and their operating system, but the necessary investments aren't being made to sort of keep up with where we need to go. Right? That's the part I'm worried about.
So
Can I answer?
if we go back,
I was going to say, I'm
Okay.
still at the kiddie table, man. I finally, the cloud guy gets asked the question and everybody else answers first. Jesus. My Tommy Tippy cup just fell
Yes.
over. Jeez, a Lou. 240 pounds. You know what I look like at a card table with a folding chair? This is not pretty. So, 2 points here. One, relative to cost and zeros and some of those other things. A lot of people have seen it, but I think a good illustration of where cloud is right now, and this will speak to the ISV question, but where cloud is right now is that if you take a look and you go search on Novartis AWS, the problem that we solved for Novartis a year ago or so was it wasn't a cost problem. It was that they needed 50,000 cores and they had 7,000 internally. And the reason they needed 50,000 was because they had a researcher that said, I think we've got line of sight to a couple of promising compounds, but I need to be able to run on all 50. right? And so 2 weeks later, we had it running, right? So this was, yeah, peak problem, right? Right. But the reality of it is that the value that was generated out of that, because what Jimenez, who's the CEO of Novartis, knows about that experiment was not 50,000 cores or any of the stuff that we think is cool. It's that 3 new promising compounds were discovered because they did something they could not do 6 months before, right? So it furthered the argument that you all are making within P&G in terms of what the value of this is. So that took it off the table. There's another piece of this that's critical about what, certainly what our software does, but software that is managing workloads somewhere other than internal infrastructure, which is that we've now got telemetry to be able to tell you exactly how many core hours against that workload, which is something that the ISVs really never had before. So part of changing some of the pricing model is going to be, I mean, quite frankly, the ISVs needing the telemetry to even be able to have verifiable data that they could validate and price against something like that. And so what I think should be, not should be, it is very encouraging. ANSYS put out a release today about an offering that they've got in terms of now pushing some of their tools out to being able to be leveraged off of the public cloud to give people the ability to burst who could not burst before. Now, there are no vendors that are listed in that release, but I'm quite intimate with the details of it for obvious reasons. But to me, this is going to be an iterative process that we're not going to solve in the next year. But the cool thing is and this is based on conversations that we're having with multiple ISVs, is that by being able to supply them with the telemetry of a per hour basis, they now at least have the tools, not sure if they have the will, but they at least have the tools to be able to do that, which is going to put the entire community in a better position to say, let's try to find a way to meet in the middle, because there is an economic formula for them that helps them grow their revenue based upon a per hour, per day, or some other basis. And so I'm very optimistic that the ISVs are going to be able to get there with some of the conversations we're having and the tools we're doing.
We have an optimist in the room.
Not my nature, but today's a good day.
Maybe to restate what you just said, that I think is what Per said earlier, is you're speaking about telemetry and maybe some middleware that's going to change how we use the other application software maybe in a smarter way. And Per, I think you had acknowledged that, yeah, maybe we do this middleware Tesla style that actually can manage these heterogeneous machines in ways. So I've heard 2 of you now say there's something else going on in the middle there that's not the application software and it's not the chip that's going to change the way in which we compute.
Mm-hmm. Absolutely.
We're going to compute smarter, you're saying, if we get the right middleware going. And
It's compute differently. I mean, these are whole new classes of problems that really don't exist today. Well, I guess they exist, but they haven't been developed yet. And I think this level of middleware is what's required, as I mentioned yesterday, kind of gather data from these new sources, not just sort of fixed satellites and what have you. And I think there's a lot of new industries that are being created out of this as well. And it's that sort of data aggregation and service delivery that middleware will enable.
So I think that one of the things that people who are thinking cloud, whether you do it with us or not, if you're thinking cloud, there's a fundamental difference between how we've typically looked at our infrastructure to this point, which is how can I maximize what's sitting on my floor? How can I make sure that I'm wringing every measure of efficiency out of the infrastructure that I have capitalized and deployed internally? What happens with cloud native software is that it's an entirely different thought process. You're thinking, okay, how do I go capture and orchestrate what are essentially infinite resources, which is a fundamentally different problem. Right, exactly. Yeah, right. Your words, not mine. But that's what's awesome about it, is that, to Tom's point, they are highly commoditized, widely available, with very flexible price point resources that are available. But that's also the challenge, is how do you corral that, not only from a technical perspective, but quite frankly, if you are running a P&L, how do you make sure that the users do not run amok? Because just because it's there doesn't mean you should use it. And I've got teenagers, right?
I also think I heard a question or a statement or an acknowledgement in there. Tim, you said that, gee whiz, there's 3 new compounds that came out of something, had access to 50,000 cores, ran it, learned something. But yet we heard a little bit yesterday about this difference between the research computing and the production computing. So is the aha moment, is the cloud more suited for the discovery? Let's put this even to the audience. What has the value for paying for that software stack? Is it the research side for the discovery, or is it the production side, or are those simply really two different models that need two different kinds of computing?
Well, there was a lot of discussion yesterday about CapEx and OpEx, which is the great question around this, right? But the reality, just to really simplify it, where we are right now, we're just solving the problems we can solve with the tools in the bag, right? And I think that what we're doing is we're putting together a base of knowledge that says, okay, this is what's possible today. This is what we're going to be able to do over the next 2 or 3 years. But the reason that I call it CapEx and OpEx is because most of what we're doing right now is coming from the lines of business, right? Because we're enabling the line of business to go get a problem solved that they couldn't solve before, as opposed to these being huge capital projects over multi-year with so right now we've got the flexibility to go do things. And so what I would say is that we are learning a lot from a research perspective, but we are doing it all on the backs of production workloads. This is just for psychocomputing, right? But we're learning a lot to go back into the research community, but it is on the back of production jobs that need to be run in order to get an answer relative to drug discovery or parameter sweeps on hard disks or CCAR runs for financial services institutions or whatever else it is.
So are you also seeing that the lines of business can make the decision to spend in an OpEx way to get stuff done that touches the product, but that the CapEx actually requires a higher level choice inside the company and we heard a little bit from Mayo a bit and some others here that, my goodness, the IT guys who are in the CapEx business don't run my HPC very well, so hence the CapEx doesn't necessarily solve the problem in this. So are you seeing a difference in where those decision points are made?
Well, the nice thing is that everything that we do is in conjunction with IT, right? So whether it's Steve Lister at Novartis or David Hines at HGST, these all folks work very well with their lines of business, right? So these are, and I think that's the key. I think it's just the culture of how those folks are operating is that the lines of business are entrusting them to make the right decisions because those folks are thinking about getting the answer as opposed to necessarily building out infrastructure. Not that there's anything wrong with building out infrastructure per se, but it's just that it's a cultural thing, right? As opposed to, I'd like to have it be an MBA answer, but the reality of it is that where IT and lines of business work well and the HPC folks work well together, they get to take advantage of cool stuff like this and make good things happen, and then everybody's successful because of it in terms of the actual business results that are generated.
And nobody knows how the memory was actually allocated in the chip in the process.
I certainly don't.
But there will be middleware that'll do it.
Yeah,
Middleware.
somewhat.
Okay.
That's right.
More questions from the audience? Anything? Michelle.
What about storage? You're talking about all this. Okay. You're talking about all the putting data on the cloud or putting compute on the cloud and then putting compute on some clusters and then using HPC, and you're getting larger and larger data sets, more and more files, trying to move all that data around. It's not fun. Middleware doesn't solve it for you. It's difficult. It is currently a very human-intensive process to get all that data around and make sure it makes it where it's supposed to go and you curate it and et cetera.
So
Go ahead.
I'm sorry.
We heard yesterday from a couple of the panels that no human should be involved in the data management, but it doesn't exist yet. Dave was one of them that said that. What do you guys think of that and where that's going?
Well, I think the title of this panel originally was Future Shock, so we get to go off what anyone's actually doing.
Go off the reservation. That's cool.
And we can start thinking about the possibilities. But there are a couple of things we know are going to happen. The first one is we know that the fabrics themselves are going to increase at a massive rate in performance, and people are going to look at that not only node to node performance, but an awful lot of it has to do with dealing with the storage system and integration of parallel file systems with the fabrics in ways that can move data around a bit more effectively. So we kind of know all of that's going to happen. But I think the real opportunity is going to be what people can end up doing with the idea of where the data is stored and where the storage system actually runs. I mean, are we forever bound to a dedicated storage cluster somewhere at the other end of a thin pipe? Or are we going to be able to, as memories evolve, are we going to be able to store more things on node and have more virtualized file systems? I think there's a lot of really cool innovation we're going to see over, give us 6 or 7 years, and the paradigm of storage could actually change. So, in the meantime, like I said, there's going to be a lot of incremental improvements to try to, make the software easier to use, more robust, allow data to move around where it's currently moving. But I think that there are really, one could imagine really cool and disruptive ways of dealing with the storage problem on a slightly longer event horizon.
Yeah, I mean, I speak with our storage division or researchers, and they actually will argue that there's almost more rapid change and disruption going on in the storage part of the industry than anywhere else. I mean, just solid state devices, use of, like I said, non-volatile memory, deeper hierarchies, custom APIs, software level APIs for storage access, and yeah, I think it's undergoing dramatic change, and I think that is probably one of the areas that'll have one of the biggest influences on the workflows, right? It's sort of, again, what I was kind of touching on yesterday. These different sort of characteristics of the data, and that really has a major impact on the infrastructure, but also the applications that build on top of it.
So I'm not a storage person, but whenever I go to meetings, there seem to be 3 things that people seem to bang their head on. One is the bandwidth growth with the capacity. But people seem to try to find out how they can grow the bandwidth as they grow capacity. At this point, we're not growing our bandwidth nearly as well as our capacity. So that's a huge problem kind of brewing, right? The second one is the amount of compute that you can do proportional to your capacity, which is related to the bandwidth, but whether or not you can get compute to be close enough to the storage so that you can grow your net compute along with the capacity, that's a second problem that people don't seem to have a really good solution yet. And the third one is actually really hairy, and I think it's probably going to really require us to rethink about all the infrastructure. That is, we currently think about storage as a garbage can. So we kind of, we throw things into the garbage can and then we eventually fish it out. But so that's the serialization, deserialization, mentality. And what really should happen is that these things should be, stored in a way that they should be stored as data structure, not just kind of, all kind of, smashed together garbage. So, but whenever you have usable data structure, you have pointer values, you have, linkages and so on. And whenever how do you map that into these, the real compute processes and so on? We don't have a real answer in any of our current infrastructure. So those are the things that, if I were going to, run a research program on storage, I will fund those 3 things. Oh.
The short version is we include data management as part of, we look at it as workflow, not compute. So I'll catch up with you later, but we've got a product rather imaginatively called Data Manager that is in charge of intelligently scheduling the data between, in AWS's case, S3, and moving some of it off to Glacier, but being able to do it so that you're only moving exactly what you need rather than paying to move bulk storage to and fro. But the bottom line is that the ability to move storage is the single largest gating factor to people being able to effectively use public cloud to do all these cool things that I've been talking about. So the good news, if you're worried about that, is that the cloud service providers don't get to fill up their compute if they don't help solve the data management problem. That's why I want to call it a storage problem, the data management problem. But there are answers out there, so we'll circle up, and I'll point you in the right direction for a couple of them. Not too many of them are free, though.
It is the top of the hour, so want to thank this panel. This has been exceeded my expectations. In fact, stellar panel, including you, Tim. Let's thank the panelists, please.